Good morning and welcome to this small session on hierarchical reinforcement learning. The last few sessions we have learned what is sequential reinforcement learning. That means we have discussed reinforcement learning with the help of the complete reinforcement environment as a single entity. Now we are going to discuss the basics of hierarchical reinforcement learning and one of the popular HRL framework known as MAXQ. And the coming sessions we will discuss another hierarchical reinforcement learning framework like options framework, and then we will discuss harm framework in this HRL setup. Anyway, these slides give you an eligibility trace that will pop up for immediate learning. The main points under discussion are grounds for HRL. Why we are thinking about this hierarchical reinforcement learning. Second one, this definition, and then we look into the popular framework known as MAXQ. The three important challenges faced by reinforcement learning are sample efficiency, scaling, generalization and transferring learning. The sample efficiency means in order to get the agent trained, we have to repeat the episodes to a minimum number of levels. That means we need more samples to get better training or better learning for this agent. For a large reinforcement learning environment, it may not be practical. If we can cut or divide the entire reinforcement learning environment into small parts hierarchically, and learning from one level will develop a higher level of knowledge to this agent, and then this agent visit next level in the hierarchy. In that situation, the agent will learn about this environment in a more good way. That is the idea behind this hierarchical reinforcement learning. At present, the reinforcement learning or sequential reinforcement learning do not have that facility. So the challenge can be addressed with help of hierarchical reinforcement learning. The next point is scaling. In a reinforcement learning environment, number of states and actions may be more than lakhs. In such situations, the agent will take much time to get a complete information about the environment. So in order to get a better learning, it will take much time, and so inline activities like games will be hang on. So the scaling was one of the major hindrances faced in usual reinforcement learning. We can face this issue with the help of hierarchical reinforcement learning. That means we divide the entire state space and action space into subspaces hierarchically, and the learning part from one level will be transformed into other level, and so automatically the learning will move in a faster way. So this same idea can be helpful to generalize the learning process and transfer learning from one level to another. So these major hindrances can be addressed with the help of hierarchical reinforcement learning. And also, in addition to this hierarchical reinforcement learning will help us to introduce the concept of abstraction. Instead of giving all the actions explicitly, we can wrap up related or connected actions together. So this type of abstraction give more meaning. For example, suppose we are going to prepare a particular dish. There are various states, and in each state there are some connected actions. For example, cutting vegetables. In that case, we will do the cutting process in a particular manner. We cut vegetables in a particular order. In that case, it will bring together and it creates a abstraction for a set of actions. This concept can be introduced with the help of options, as Richard A. Sutton given in his textbook. Now we move on to the promises of hierarchical reinforcement learning. In hierarchical reinforcement learning, Instead of looking for a single policy to achieve the goal of the task, several sub-policies that work together in a hierarchical structure. So instead of looking for a common policy that will satisfy all the states, we divide the entire state space into small subspaces, and we divide the goal into sub-goals or sub-policies, and the agent will move from one state to the end state according to these sub-policies on different levels hierarchically. So the task can be divided into sub-task, and it can be conquer like divide and conquer rule. That is the advantage of using hierarchical reinforcement learning. Then we move on to the first framework in hierarchical learning, known as MAXQ. This Max is one part, Q is another part. We will explain what is Max part and what is Q part at the end of this presentation. What is the objective of MAXQ framework? Solve a Markov decision process M defined over a set of states S and actions A, with the reward function R of S dash given S comma A, that we are familiar with our MTP and Bellman equation topic in module 3, and the transition probability function P of S dash given S comma A, that means the probability for selecting this action A from state S to S dash. These are the basic idea of MAXQ framework. My aim is to solve this MTP. We know one approach, that is a sequential reinforcement learning approach. We can use Bellman equation and solve it. Now we think about dividing this entire reinforcement learning environment, that means the state and action space, into hierarchically subparts. Then we apply the learning sub-policies on each of these subparts so as to get maximum return. Okay, we look into the details. So this graph represents the MAXQ. This is called the MAXQ representation. So this V naught pi of S defines the policy, pi defines the policy, V naught of S defines the state value, the return at this max node 0. This node is called max node A1, and this node is called max node AN minus 1, etc. Automatically this is the terminal node, it gives the return R1 from the terminal state. Now this R1, R2, R2, R3, R4, R5, etc. are the returns for choosing this action AN minus 1 at the state S with this action AN, like that. Now the concept of hierarchy means this V naught pi of S is calculated using this V A1 pi of S. So V naught pi of S called the next low level hierarchy V A1 pi of S, and V A1 pi of S called the next lower hierarchy, like that. So this defines the hierarchy for our Markov decision process environment. And also there are this, when we draw a small square here, we get two parts, the left hand and right hand. The right hand defines the Q value. The C naught pi of S comma A1 defines the Q value. It stores the Q values corresponding to this choice of A1. It is like a memory slot which stores all the return for choosing this action A1 from state S and leads to the rewards R11, R12, R13, R14, etc. And so we can make use of the concept of MTP here. The difference is that we divide it into different nodes, and these nodes divide this entire MTP into subroutines, and these subroutines will be optimized hierarchically. Let us look into the details. Formation of MAXQ method. There are two ideas. One is max node, another is subtask. In the previous figure, this is called the max node, and this left side, when we draw a square or a rectangle like this, it creates a subroutine or subtask. Each max node I corresponds to a separate subtask Mi. M stands for underline markdown, underline Markov decision process. That is why we use M. Mi means ith subpart. The children of max node I are the actions of Mi. See, the children is a tree structure. The children of this max node I are the actions of that particular subtask Mi. In the previous figure, this is our max node. These actions are called its children. Splitting of state space. How we can spread the state space using this hierarchical structure? Each subtask Mi divides the set S, that means the state space S, into Si Ti. That means this Si is corresponding to Mi, this particular subtask. Si means non-terminal state corresponding to the ith subtask, and Ti means T stands for terminal. Terminal states corresponding to this ith subtask. Then there is a condition that S is equal to Si union Ti. One more condition, Si intersection Ti is equal to 5. Si intersection Ti equal to 5 means they are disjoint. They are disjoint sets. Now these terminal states again divided into two parts. One is Ti minus Gi, another one is Gi. Then Gi is called the goal states for this subtask Mi. Then Ti minus Gi is the non-goal states. That means this agent choose action so as to maximize its return. So the agent moves through those states which gives maximum return, and ultimately it may not visit all the end states. Sometimes the some of the end states does not give maximum return to that agent in one step movement. In that situation, it will choose an action greedily and it moves on to the end state which gives the maximum return. That is why we call it as Gi, the goal state, and Ti minus Gi are known as non-goal states. There are two types of terminal states. One is non-goal states, that is Ti minus Gi, and goal states Gi. See, our aim is to divide the state space into different partition. One is non-terminal state corresponding to each subtask. Another one is terminal states. But terminal states are also of two types. One is goal states, another one is non-goal states. That's all. Now let us define the hierarchical policy. Now see, I split the entire task into subtask. Each subtask will follow a policy. That policy is called the sub-policy or hierarchical policy for MAXQ. We have seen it from the MAXQ graph. It is denoted by a family pi naught, pi 1, pi 2, etc. pi n. That means there are n hierarchical policies are there. From pi naught, the agent will learn something from that substate, then it will goes to the second level, substate M2. Then it moves on to M3, like that. So the hierarchically the learning will happen. So at a time we just focus on one subtask, and so number of states and actions are minimum. So automatically the agent will learn in a fast way. That is the advantage of using this hierarchical policy. Okay. Now we are going to define the state values of MAXQ framework. As in the case of MDP, we are going to define the state values and the state action values or Q values. Since it is an MDP which divides the entire problem into subtasks, we can make use of the same rules. So for each subtask Mi with the root state S, that means it divide from the root state S. From state S, it is split into two subtasks S1 and S2. In that case, Vi pi of S, that means I stands for ith subtask. Vi pi of S is equal to the immediate return for choosing this action A, that is Va pi of S plus this is the expected value for choosing this action move into another states S dash. So it is sigma over all S dash, the probability for choosing this action A from state S to S dash into the value corresponding to that state S dash. This defines the expected value of return in one step bootstrapping. Then the Q value formula. The V formula starts with the state value formula starts with Va pi of S. Here also qi pi of SA, here we are giving importance to the action A. See, we have seen this idea in MTP and also temporal difference learning. The action values are more important than state values when this agent will choose some exploration. That is why we choose the action along with the state. So as in the state value, the first part is VA pi of S plus second part is known as completion function, or it is a cumulative sum of returns, that is Ci pi of SA. That means at the ith sub node or subtask under the policy pi for the action A from state S, the sum of all returns for this ith subtask. This is the Q value corresponding to the children. Then VA pi of S is corresponding to the max node, internal max node, where this VA pi of S is equal to, it has two values, namely QI pi of S comma pi I of S if it is a composite action. See, A is a composite action means from the state S, the agent will take an action A and it may move to different states S dash, S double dash, S double triple dash, etc. So the movement from the state S through A leads to different possible states. That is called a composite action. Sometimes this action A leads to the terminal state. In that case, it is called a primitive action or similar single step movement. So QI pi of S comma pi I of S, pi I of S is simply the action. Then this is the if I is a composite one. If I is a primitive one, that means the end terminal. In that case, it's a sum of all probabilities into corresponding rewards. Let us look into this figure. See, this one is our primitive action. That means it leads to the end terminal. So R11, R12, R13 and R14 and returns for this movement from state S to the terminal state through the action A1. So we have to calculate the expected return as the probability for choosing this action A from S to the terminal state into corresponding reward R11. Similarly, probability for choosing this action A1 from state S to S double dash with the return R12, like that. So that is the formula here. This S dash may be any end terminal state. Then what is the completion function? Ci pi of SA is equal to, starting with this value, but in that case it is not a terminal state, so we have to use the state value for the state S dash. So this is the average value of returns sigma over S dash P of S dash comma S dash given S comma A into Vi pi of S dash. That means the state value corresponding to all those states S dash originating from S with the action A in the subtask I. So this is Ci pi. It is called a cumulative or completion function. So the Q value contains two parts. One is the internal max node value, that is Va pi of S, and this is called the completion function or Q value function. That is why it has the name MAXQ. Value function semantics for MAXQ framework. The declarative semantics or value function semantics for MAXQ framework is with the name MAXQ. One is the max node return and Q is the cumulative value return or Q value stored in a memory slot. Each Q node with the parent I and the child A stores the information Ci pi of SA. That is called the Q value. For each state S in the substates Si for the subtask I, Mi. Each max node I returns the Q value of the child chosen by pi I. When we look into this plot, this Va1 pi of S defines the q value for the child. This v0 pi of s gives the q value corresponding to the corresponding to the state s in Si. That is why it is called max q. See, this q part is for Ci pi of Sa, then max node value corresponds to v pi value. See, this v pi value. This is max value, this is q value. That is why the name max q. This is the max, this is the q. The value returned by max root is, then how we can calculate the max root value? That means we split this entire MDP into different hierarchical subtasks. Then how can I calculate this max q value? This root node max root 0. For that, you just go through the left direction. That means this max root calls this one. This one calls the next max root, internal max root, and it leads to the end terminal root VAN pi of s. So we have to calculate VAN pi of s. It will goes to the higher level max node. This max node take this value, this q value, that is C pi an minus 1 of s comma n. Then this goes to the next higher subtask. It will add this q value, that is ca1 pi of s comma a1. Then it goes to the max root node 0. Then it add this q value, that is z0 pi of s comma a1. So we just add these values, v pi an of s, c pi an minus 1 of s comma an, etc, and c0 pi of s comma a1. Look into this, v pi an of s plus c pi an minus 1 of s comma n, etc. This is called the max root value. In this way, we can calculate the highest hierarchical state value with the help of this max q operation. This is one of the simplest reinforcement learning, hierarchical reinforcement learning framework. Then there are two popular theorems that ensures that this representation of this tree diagram for max q is unique, and these q values are uniquely determined. So first of all, representation theorem for values, that is for our declarative semantics. Let pi is equal to pi 0, pi 1, pi 2, etc. pi n be a hierarchical policy defined over a full state max q graph, as we have seen in the previous slide. Let I is equal to 0 be the root node of the graph. Then there exist values Ci, that is internal max nodes, and Vi for the primitive leaf max nodes, that means the last terminal one, such that V0 of s is the expected cumulative reward of following policy pi in the state s. That means this definition is valid. We are using that theorem to calculate V0 pi of s as the sum of this leaf node state value plus the remaining q values. It is uniquely determined. That is one of the first theorem in MAXQ framework. Second one is the tree diagram is unique. Uniqueness of representation. For all max nodes I, actions A, states s comma si, s in si, and distinct states s1 s2 element of result of our subtask I under the policy pi with state sa. That means it's a return under the policy pi for the top subtask I at the state s with the action a. Remember, this s1 and s2 are in this same hierarchy. Whenever ci pi of s1 comma a not equal to ci pi of s2 comma a, that means the internal q values are not equal. It is the case that xi of s1 comma a not equal to xi of s2 comma a for value abstraction xi. The idea is very simple. If s1 and s2 are in the same hierarchy and their q values are not equal, then the values are determined by different functions. That means Whenever two hierarchies, that means two hierarchies gives the same value, same Q value, then the representation is same. One may be some different assignment of a state and action values. That means this representation is uniquely determined. Whenever two states S1 and S2 are from the same hierarchy, then if the state values are, the internal Q values are not different, not same, in that case the corresponding value functions are not same. That means the representation is unique. This is all about our first framework in reinforcement learning, that is called MAXQ framework. Next is options framework. It is developed by Richard A. Sutton, the father of modern reinforcement learning theory, and it developed a new concept of options rather than our primitive actions or one-step actions. One-step actions, the agent will take an action from a state S and leads to next state S dash. But sometimes a single action has no meaning. We have to consider a set of connected actions to get a complete result. For example, suppose we have to walk through a particular surface, our muscles will contract and expand, and our human pose will work accordingly. Not only we can walk over a particular surface or on a road or anywhere. In that case, just a movement of our hand or movement of our one leg need not facilitate the action. Our action means moving from one point to another point. It will demands lot of other associated actions together. So all these associated actions together known as options. This idea developed under the options framework, and it devises a new concept of hierarchical reinforcement learning. We will discuss that idea in the next session.